So to take an element from the queue, all we have to do, to declare a queue, basically, let's start with the declaration of the queue. So to declare a queue, we basically have to allocate a queue. And we said that every queue has a front and a back pointers, as well as a size integer. So we're going to make the front points to null, the back points to null, and the size 0. So let's do that. So we're going to create a function which will create the queue. So it should be of type queue pointer called create queue. It takes no parameters, and it create a queue, and it allocate memory for that queue. So that's of queue pointer type malloc size of queue. So that will allocate memory for our queue structure. Now the queue back and the queue front, both of them takes null, and the queue size takes 0. So after declaring this queue, all we have to do then, we have to return it. So let's return that queue. Cool. Now the next thing that we need to do is we're going to have to create a function which will test whether the queue is empty or not. So it's of type bool empty queue. It takes a queue pointer, and it returns whether the queue size equals 0 or not. So if it is equals 0, then it'll return true, otherwise it will return false. Cool. So to add an element to the queue, to push an element to the queue, we're going to have to do the following. It's really similar to the stack, except that now we're dealing with 2 pointers to keep track of the location of the queue nodes. So whenever we want to add an element to the queue, we have to declare a new queue node. So let's say we want to add the number 5. So we have to declare a new queue node. So that's a queue node. And we have to copy that 5 inside the queue node value. So that's 5 there. And the next of that node should be null, which means that this node doesn't have any next. Okay? And now we have to connect this node to our queue structure. Okay? So there's 2 possibilities. If the queue is empty and if the queue is not empty. If the queue is empty, then we have to make the front element and the back element both points to the same queue node. Okay? Now if the queue is not empty, let's say we have a non-empty queue. So here's a queue. So this queue is not empty. This queue has both front and back points to the same node. Now if we want to add another element, say 6 to the queue, then we have to create that node. We copy that 6 into its value. So that's a queue node. And its next would be null. It points to null as a next. And then we go to the last node pointed by pointed by back. So this is the last node pointed by back, this one here. We make its next to be the newly created node. Okay, so instead of null, it'll point to the next newly created node. And then for the back, instead of pointing to the old node, the back will point to the newly created node. Okay? And now we have a queue that has front points to this first node, and the back points to another node. Again, whenever we want to add another element, we just create the node, we put inside it the value, let's say 7, the next would be null, and then the next of the node pointed by back would be that node instead of null, and then the back would point to that newly created node and not the previous back. And so on and so forth. So let's implement this primitive, let's implement this function using real code, using the C language. So the function's name would be something like pushQ, and it takes a Q pointer, Q, and it takes value, and basically the first thing that we're going to have to do is to create the new node, so the new Q node, so that's Q node, pointer, Q node, equals a Q node pointer malloc size of Q node. So we allocate space for one Q node and we copy its address to the Qn variable. And the Qn variables next would be null. The Qn value would take the value parameter of the function, and then the Q size would be incremented. Let's increment that, the last thing, so the Q size would be incremented here, the last instruction. And then before that, we have to link our newly created node with the Q. So we said that we have two possibilities. Either the queue is empty or the queue is not empty. So if the queue is empty, then we have to do two instructions. We said that the first thing would be to make the queue back next, make that points to the newly created node instead of null. So that would point to Qn. And the second instruction would be to update the back pointer. So Q back would take the newly created node, and then finally we would increment the size of the queue. And that should do the job. So this if the queue is not empty. Okay, the line that I wrote here is if the queue is not empty, then we would do this. Now if the queue is empty, all we have to do, so this is for else, so that's else. Now if the queue is empty, all we have to do is basically we have to make the front and the back of the queue, so that's back equals queue front, so both of them would equals that newly created node, Qn. Now let's try to compile this. Now it's compilable. So we have to write our final function which will remove an element from the queue in order to be able to test whether we did it correct or not. So in order to remove an element from the queue, all we have to do is basically, let's draw this queue data structure here. So here we have the size, we have the front, and we have the back. Now the front points to some node here, which points to the next node, which points to the next node, and so on. And the final one points to null. And we have our back points to that very last element. So if we want to remove an element, to pop an element, then we're gonna pop from the front. Okay, so we add to the back and we pop from the front. So that's first in, first out. Okay. So the first thing that we have to do is we're going to have to create a variable called value, which will take the content of that variable, of that node, of that Q node that the front pointer is pointing at. Okay? So we're going to take that value. Let's say here we have 6. So basically here we're going to copy inside value the number 6. Now we have to make a copy of the address of that node, the node that we're going to remove. So we're going to create a Q node pointer that will contain the address of this node. Okay, so the address of this node. And then we're going to update the front node to take the next of its node, of the point that is pointing at. So instead of pointing to this node, we're going to point to its next. We're going to point here. Okay? And since we have the address of that node that we're going to delete, we can delete it. So we're going to free qn. So that's free qn. And finally, we're left off with a queue that doesn't have that node on the left, and we're left off with the rest of the nodes. And then finally, we return that value that we have popped out. So let's implement this idea. Let's write it, see if it works. So we said that we're going to create a function that returns an integer. The function is called popQ, and we give it Q pointer and nothing else, just the Q, okay? And the first thing that it has to do is to declare a variable called value. That value will take basically the Q front value. All right, and before taking that value, let's test whether the queue is empty or not. If the queue is empty, then we're gonna stop. We're gonna just print an error message. So if the queue is empty, then we're just gonna print f an error, queue is empty. And then we're going to return 0. Okay? Then after retrieving the value from the first node, the first Q node that our Q struct is pointing at, we're going to have to copy the address of that first node. So Q node pointer Q node equals the Q front. And then we're going to update the Q front. So the Q front takes the Q front next. And now we have to remove that qn that we've saved its address. Okay? So we're going to free qn. And then of course we have to decrement the size. And finally return that value. And basically that's the idea. So let's see if it works. So I'm going to go here to the main function and I'm going to create a queue. So that's a queue pointer, which will take create queue. And the next thing that I'm going to do is I'm going to push to the queue some numbers and then try to print them out to see if they get printed correctly. So I'm going to push 5. Let's push another number, 7 for example. And let's push another number and 9 for example. So that's Q9. And now I'm going to iterate through the elements of the queue, I'm going to keep extracting popping elements, popping numbers, and printing them. They should be printed in order. So while the queue is not empty, the queue is not empty, we're going to printf an integer and a tab, and that integer would be something that we're going to pop from the queue. And let's compile and run. And as you can see, the numbers gets printed correctly. So that's 5, 7, and 9. And basically that is the queue data structure. So it's pretty basic and pretty straightforward. Now, as you can see here, if I get back to the sketch here, the complexity of this data structure, what is the complexity of this data structure? Whenever we want to add a node, whenever we want to add a number to this data structure, we're only doing one operation. Just create a new node, and then you point to that new node, and of course we fill it with its values. So we're doing a constant number of instructions, okay? So this is order 1. So adding elements is order 1. Now retrieving elements is doing the same thing. We're extracting some numbers, and then we're changing a couple of pointers, and that's it. So that's also a constant number of operations. So it's order 1. Creating the queue is also order 1 because we're doing some constant number of operations, and testing whether the queue is empty or not is also a constant operation. So our data structure is very efficient in terms of adding and removing elements, and all the primitives that we've implemented so far are very efficient and can't be improved any more. So they're so efficient. And the same thing for the stack. We're always adding to the top and removing from the top. There is no loop, there is no iteration there. So basically all the operations that we've been doing are order 1. So the stack that we've implemented is very efficient in terms of space and time. And also the queue here is in terms of space and time. It's efficient in both terms. And that's it for this video. See you next time.